Hello students. So this is the springs video part 2. In the previous part we have discussed some of the applications, some of the types and some important terms used in compression springs, and we were discussing about the spring index, which is written as C, which is d by d, and spring rate, that is load upon deflection. Now we will discuss the concept of pitch. The pitch of the coil is defined as the axial distance between adjacent coils in uncompressed state. So when your spring is not compressed, there is a gap between one coil and the other coil, as we have discussed in the threads. So this distance from one coil to the adjacent point of the next coil, this gap is called pitch of the spring. So pitch P is written as free length divided by n dash minus 1, or the other formula we can use is free length minus solid length upon n dash plus d. Now we will discuss the end connections for compression helical springs. End connections for compression helical springs are suitably formed in order to apply the load. So when we use springs, we have to use in some kind of application where the load will be applied on the spring. So our end connections will depend upon the application in which we use springs. So you can see the difference. This is plain end, this is called plain end, and there is the grounding has been done, grinding, and it is called ground ends. This is a completely straight, that is squared ends, and this one is squared and ground ends. So there are four common methods which are used in forming the ends of the helical compression springs. So four we have discussed here: plain ends, ground ends, squared and ground ends. The turns at the two ends do not contribute to the deflection due to load. So you can see in this square end, since your spring is straight, and in this squared and ground end, since your spring is straight, it will not contribute to the deflection. Means this turn and this turn will be neglected because it does not contribute to the deflection. It is already in a straight position. While in this case, this turn is not straight, so it will contribute to the deflection. Similarly, this case, the turn will contribute to the deflection. So therefore, while calculating the number of active turns, the end turns should be subtracted from the total number of turns for different style of the ends. So what does it mean is, for plain ends, total number of turns will be n. All the turns will be contributing towards the deflection. For ground ends, again all the turns will contribute to the deflection. For square ends, we will add n plus 2 because the upper turn and lower turn will not contribute to the deflection. So active turns will be n, but total turns will be n plus 2. Similarly, for squared and ground ends, the active turns will be n, but two turns will be inactive, the upper one and lower one. So total turns will be n plus 2. Now discuss the formulas that we will use in the numerical problems. You do not have to go through the derivation. Just we will see how these formulas are derived so that we can use in numericals. The important thing is you should know the formulas so that you can use in numericals. So stresses in helical springs of circular wire. So this is your spring load acting W of diameter D and wire dia small d. So this is axially loaded helical spring. So it will apply a force, that is torque or shear stress on the wire. So what will happen is, let capital D is the mean diameter of the coil, small d is the diameter of the spring wire, n is the number of active coils, g is modulus of rigidity, w axial load on the spring, tau maximum shear stress, c spring index, p pitch of the coils, delta deflection. These are the parameters which we will use in the numericals, so you should all know what denote capital D, small d, and you should all be aware of this. So load W tends to rotate the wire due to twisting moment. Thus torsional shear stress induced in the wire, that is torque is load into radius, force into radius, and torque is written as pi by 16 tau d cube in case of wire. So from this we will calculate tau, that is tau 1, 8 WD by pi d cube, very important formula. 8 WD by pi d cube will be the shear stress. In addition to torsional shear stress, the following stresses also act on the wire. First one is direct shear stress due to load W, shear stress due to curvature of the wire. So first one is direct shear stress, which is tau 2, load upon area. Load is W, area is pi by 4 d square, so it is 4W by pi d square. So we will add maximum shear stress, torsional shear stress plus direct shear stress. 8WD pi d cube we have derived earlier, 4W by pi d square we have derived, and we will simplify it. You do not have to go for the derivation. You will get this result, 8WD by pi d cube 1 plus 1 by 2c. This 1 plus 1 by 2c is written as Ks, and it is called shear stress factor 1 plus 1 by 2c, and this is 8WD by pi d cube will be your shear stress. So final formula will be Ks 8WD by pi d cube, where Ks is 1 plus 1 by 2c. But when we consider the effect of curvature of the wire, then the formula will be same. Shear stress is equal to K 8WD by pi d cube. Instead of using Ks, we will use K. The K is called Wahal factor, and this is introduced by A.M. Wahal, and it is called Wahal stress factor K when we consider the effect of curvature. Then the K will be written as 4c minus 1 by 4c minus 4 plus 0.615 upon c. So this is the formula for K, where C is spring index, that is capital D by small d. So the Wahal stress factor K may be considered as composed of two sub-factors Ks and Kc. So Ks into Kc will be K. Ks is stress factor due to shear, and Kc will be stress concentration factor due to curvature. Another formula that we will use in the numerical is deflection. So we will apply the torsion equation, T by J is equal to tau upon R into C theta or G theta upon L. From this relation we will get theta, and this is TL by Gj, where J is polar moment of inertia pi by 32 d raised to power 4, and G is modulus of rigidity. You don't go for the derivation, just I wanna make you aware that how these formulas are derived so that you can use in your numericals. So in theta TL upon Gj, you will put the values of T, that is load into radius, L is pi dn, J is pi by 32 d raised to power 4, and G, and the relation will be 16W d square n upon GD4. So this is your delta, and delta will be theta into d by 2. So its final relation for the delta 8WC cube n by GD. So this is the relation you should have to remember for the numericals. So next we will do the numericals, but we will do it in the next part of the video. Thank you, students.